Okay, I think we'll get started. So we've been doing some stuff with Coulomb's law, charges, all classical. We're building ourselves up towards hydrogen now, and we will need shortly to move to full-blown quantum mechanics to actually address the true nature of hydrogen. And of course, we won't do a full quantum mechanical treatment. We will just talk about the results from quantum mechanics. But today it's kind of fun to just imagine that hydrogen is a classical system. I call this the solar system model. It could also be called classical hydrogen. And what we imagine here is that the electron is orbiting the proton like the Earth orbits the sun. And this is not too unreasonable to believe because of Coulomb's law has exactly the same form as Newton's law of gravity. Now, in a normal, just regular general physics course, we would have addressed Newton's law of gravity now. Because we're focused in this work on physical chemistry and laying the groundwork to become to look at the world through the lens of physical chemistry, we have to make some cutbacks on an entire physics course, and we have done so with gravity a fair bit here. So I'm just telling you that Coulomb's law, which we've been working on, K Q1 times Q2 over R squared, if you replace that with G, a gravitational constant, M1 times M2 over R squared, you get Newton's law of gravity. And so the mathematical form is identical. So when we discovered long ago that a proton is big and heavy, an electron is light, and we knew about Coulomb's law, certainly the gravitational attraction between those two is negligible, but the electrostatic traction is quite big. And so let's just let the electron orbit hydrogen based on Coulomb's law. Now, next lecture, we'll talk about why that's a problem. But let's just let this happen, and let's see how close we come to matching experiment. Okay, so a couple of things here. We're going to need to put in numbers. So try to avoid numbers as much as we can and think more algebraically as we go through the course. But here's a case where we definitely want to put in numbers. And so we've got Coulomb's constant, got charge of an electron, we've got mass of an electron. These are all in SI units. We've got the radius of hydrogen. So this is called the Bohr radius. I'll write that down here. Bohr radius. Then we have the speed of light. And finally, we have a conversion from a unit of energy called electron volts to joules, the SI unit. And the reason for that is that when we work on the atomic level, joules is kind of an ugly number, like 10 to the minus 19. And electron volts, a much smaller value, then take on nice numbers at the atomic level. And notice this is not a coincidence that this number and this number are the same. The electron volt is the energy needed to move one electron charge through 1 volt. Now, okay, so we've got our numbers. Let's build our system now. We're going to need something we haven't talked about yet, so I'm just going to tell you about it. We will get to it in this first introductory course. But let's draw a free body diagram, as we've done. We've got an electrostatic force that, at least for the electron now, is pointed here. This will always be pointed inward towards the nucleus because it's an attractive force. But then we have something called the centrifugal force, and we will talk about that coming up. But basically, for this purposes, if you might imagine swinging some water around in a bucket, that if you can go up over your head if you're going fast enough, because the water will be will experience, will be pushed out. Now, a lot more technical than that, and we'll talk about centripetal force, which is really the force that one wants to talk about here, which is an inward force. The centrifugal force is the reactive pair to that, which is directed in the equal but in opposite direction. So I'll just tell you now that that's the mass. Oh, and I should have an A naught here. It's the mass of the electron times its velocity squared over the radius. Okay, so I'm just giving you that. We'll call that F rotational. So if we need to balance this so that we have a stable orbit, we're not crashing in and we're not escaping, then the magnitude of the Coulomb force, which is right here, and the magnitude of the centrifugal force right there should be equal. All right, well, now we can calculate some things. So let's calculate the velocity. Right? So we can solve for velocity, and we have it in terms of all these numbers. And so we can calculate that by plugging these numbers in, and we get quite fast. 2.1 times 10 to the 6th. We'd expect the electron to be moving fast. But notice we're still a significant way from the speed of light. And so we don't have to worry about things like special relativity for this going close to the speed of light. Now, if we have the velocity, we can get the kinetic energy, because kinetic energy is 1/2 mv squared. If we plug this, so we'll plug this into here, then we get our formula for the kinetic energy. We have already talked about the potential energy for Coulomb's law. We just integrate up the radius, and so let's see, we integrate up the radius here, so that becomes just the radius to the first power, Coulomb's law. And now we have the total energy, which is just kinetic energy plus potential energy. And so if we take negative this plus this is half of this, so we're going to get negative half of this again. And so here is our total energy. Well, what we can do is we can do an experiment where we strip that electron off, and we need to figure out how much energy does it take to pull the electron off. And that's called the ionization energy, because we're creating a positive ion by removing that electron. Well, the experiment yields a value of 13.6 electron volts. That's the ionization energy measured experimentally for hydrogen. So let's plug in these numbers. And notice this here, what I'm doing here, if I don't have this number, then we're going to get our energy in SI units in joules, and I'm going to divide by this number to convert it to electron volts. And so when we do the calculation, lo and behold, we get precisely 13.6 electron volts, which is a great match with the experiment. And so we would think, wow, we've got, this actually works. Well, when we push it further, and for just purely logical reasons that we'll talk about next lecture, the solar system model can't be an actual description of hydrogen. All right, well, let's just quickly pick up a couple of other things. We can pick up the period, and I've tried to make this distinction. T is usually used as the period as well. This is not the kinetic energy T here. So we have 2 pi r divided by the velocity, and we get a very short period, as we might imagine. The electron's really going fast. It doesn't have far to go. So very short period. If we take 1 over the period, whoop, I got this wrong. Didn't finish this off. we get about 10 to the 15 hertz. And if we convert that, if we were to imagine, let's imagine that this was light given off. And we will talk about next time that a moving charge will have to emit radiation, and it would emit radiation at this frequency. We can convert that to a wavelength by multiplying the period by the speed of light, and we get, I ended up erasing this, 4.5 times 10 to the minus 8th meters, which is 45 nanometers. And we haven't yet talked about the electromagnetic spectrum, but this is in the deep, deep UV. It's in what's called the vacuum UV, or the vacuum ultraviolet. So very high energy light. It's a light at a wavelength that would get absorbed by air, and that's why it's called the vacuum UV. If we wanted to use this light in an experiment in the laboratory, we would have to pass it through an evacuated chamber because it would be absorbed by the oxygen and nitrogen in the air. All right, so again, this is not how hydrogen works. It is a reasonable guess early in the history of quantum mechanics, right before quantum mechanics, and we start to get these natural measurements of hydrogen. It's reasonable to expect the solar system model based on Coulomb's law and its relation to gravity. The numbers work out great, but then as one thinks about it further, it can't be the case. So view this as just a fun little exercise, and you could try getting these numbers yourself and see if I made a mistake there. And then we'll move on to how hydrogen really works over the next few lectures.